This is a showcase of the program Damascus I made, originally for visualizing complex functions and derivatives, but I modified it so it can simulate quantum particles and their wave functions. So I was always fascinated about what complex functions over a complex domain looked like, and I built this program to visualize those. So quickly, I'm going to graph a function so I can explain how this program works. So this function is a function in the complex domain. So you can see this coordinate is the real coordinate of the input, and this coordinate is the imaginary coordinate of the input, and I can drag around the input. Up here I have color-coded balls that show the output, the derivative from the start point to the end point, and the output. So each little point has a little square, and the color of that square represents the output of the function at that point. Now, this program uses HSV color as a way to visualize the two-dimensional output of a complex function. So, first of all, the saturation of a color has to do with the magnitude of the output at any point. So here, where it's kind of gray, it means that the total magnitude of the output is fairly low in comparison to the points around on the screen. Secondly, the hue of the color represents the argument or the angle from the real line of the output. So let me show you a quick graphic. Here we can see that 0 degrees, or purely real numbers, will look red. Purely negative real numbers will look turquoise. Purely imaginary numbers will look kind of greenish yellow. And purely negative imaginary numbers will look purple. And this is all very important to showing you what's going to go on when I graph a wave function. So here I'm going to turn on physics mode, and this is going to simulate one particle in a box. It's going to look really cool. So you can see that it all starts real, and as it goes out, it becomes more and more diffuse. And eventually it's going to hit the wall, and it's going to reflect back. Now, I also added something that takes the wave function and squares its modulus, and it's going to be all purely real and purely positive. But this shows the actual probability density at any point, which I think is awesome. And you can see it waving in and out. This all uses Fourier transforms to simulate the model. And another really cool thing I can do is I can drag a lasso tool to add a big potential. So look at this. I'm going to drag around here, and then it's going to create a huge potential here, and it's going to shoot everything out. Oops. So back here, let me just adjust it so it's a little bit nicer. I can drag a potential, and it shoots out. What's even more awesome is if I change the potential to a negative, I can create a sink. So instead of pushing everything out, it'll absorb it all. So let's make it right here. And it sucks the whole wave function in here. And then I can turn on modulus squared to see what the actual probability density looks like. Isn't that awesome? Now what I can do is I can modify the initial conditions of the wave function. So say I want to have a particle that's instead traveling at a certain velocity, or we think it's traveling at a certain velocity. Now when I start the program, you'll see that the wave function radiates out this way from a focus at the very center. And I can turn on modulus squared, and this probability density makes a lot of sense because you'd expect the probability density to have a center that's going in a certain direction. And after it hit the wall, it's going to turn back and it's going to look fairly similar to how it did last time. And same as always, I can draw a little thing, and it shoots all the probability density out of that, and you can see the ripples in the wave. And now if I change this to negative, I can suck the whole probability density into a certain region that I want. And you can see all of the ripples in the waves. Isn't that just awesome? Thank you for watching.